So this is the second part of the volume by slicing, volume by disc, and volume by washer method. So just as a recap, I'm going to go back for a brief second. We talked about the volume by slicing. That was if you have a solid base, a flat base, and then you stand up slices of, let's say, a triangle or a square or a rectangle or whatever it is, you can obtain the volume by just integrating the area of the slices from the beginning of the bottom of the domain to the other end of the domain. So we did volume by slicing. Then we went on to looking at volume by discs. And this is assuming we have a region and we take this region and we rotate it all the way around the x-axis or the y-axis. And when we do that, that gives us a disk. We need to find the radius of the disk. And then the volume is just the integral of pi r squared. Okay, so the last thing we had, so everything we had done thus far was rotating about the x-axis, or here we rotated about the line y equals 1. So when we rotated this thing about the line y equals 1, it ended up with something that looked like this. Actually, that shouldn't have gone down that far, but we ended up with something that looked like that, and that we were able to find the volume of that region. Okay, so then I said, well, let's suppose we do a volume of revolution about the y-axis, or now we're rotating in this direction. So if we rotate in this direction, our disk is going to be flat. All right, it'll be flat, but it'll be horizontal disk, and it's going to move from the bottom to the top. The other discs we were looking at were like this, and they were moving from left to right. Now, if it's in the y direction, our discs are going to move from the bottom to the top. So we talked about what the formula would look like. It would be the integral from c to d of pi r of y squared, and that should be dy. It's always good to go back and look over your notes. Okay, and so now the volume is a function of y on the interval CD. So here we are taking, this was the example that we started with. We're taking the volume, I want to find the volume of the solid generated by revolving the region bounded between the y-axis. So the y-axis is here. The curve x equals 2 over y between x equals y equals 1 and y equals 4. So we got this picture right there. So I'm going to insert just a little space so I can have some more space for my thought process, and then move this down. Okay, now my picture's in a nice spot. Okay, so we have this thing. As you can see, it's going to kind of look like a bullhorn. All right, if you know, here's the spout of the bullhorn. So you're going to end up with this three-dimensional region. It's a volume, and we need to find the volume of it. Okay, so the volume of this disk is going to depend on its radius, and its radius is that length. And for this problem, the radius is always how far out you go, and how far out you go is x. If I go out this far, that'll give me a different x. If I go out this far, that'll give me a different x. So I can see the radius is always x. So for this problem, the r, the radius, which is now a function of y, is for us x, and x is 2 over y. So therefore we know what our radius is, and we also know that our domain is going to start from 1 and go up to 4. So using the disk method, I get the volume is the integral from 1 to 4 of 2 over y squared, pi times 2 over y squared. I just completely forgot everything. Come on now. All right, pi, the radius squared is 2 over y squared dy. Okay, so if your disks are on the y-axis or look like that, then we integrate dy. If your disks wrap around the x-axis or some line parallel to it, we get something else. Okay, so this is pi, the integral from -1 to 4. We can actually take the 2 out. So we can take the 2 out as 4 pi. So there we go, 4 pi, and then this just becomes y to the -2 dy. And then we're going to integrate that. That's 4 pi. I'm going to get y to the -2 will give me -y to the -1. Evaluate between -1 and 4. So this is 4 pi. I normally don't do these integrals, but I recognize that there's some people who are still struggling. So I'm trying to do a little bit better at going through them. Okay, so now 1 over y, so I'm gonna put the negative out here, and this is 1 over y. It's y to the -1, evaluate it between, and this should just be a +1. I'm not sure how I made it a -1, but it's a +1 to 4. So now I get -4 over 4 pi, and then this is going to be 1/4 -1, which is -4 pi times -3/4. So my answer just turns out to be 3 pi. Okay, so that is a volume by disk problem. All right, I have another volume by disk problem. But this one I need to draw for you. So this one looks weird. Let's see, O, A, O, A, B. Okay, all right, so here's the next one. We'll steal from my problem sheet. I think we are on problem 4. Okay. Here is problem 4. Our next problem. Give you a minute to copy it down. It says find the volume of the solid generated by revolving the region OAB about the line segment AB. Okay, so what is the region OAB? Well, let me draw it for you. Okay. So I'm going to draw the line y equals x squared. And this point is O. And then I want to draw a line. Come on now, move out my way. So here's my line, and this is the point A, and it is the point 2, 0. And of course, I never have enough space on this here. Okay, so this, oh boy, that's gonna have to stay. Okay, and this point right here is B, and it is the point 2, 4. And so this is the region that I want to revolve. So here's my region that I usually make that But yeah, that's fine. I can do it that way. So this is the region I want to revolve around the line segment AB. So here is the line segment AB is right here. Okay, so that's the line segment AB. And I want to take this region OAB and I want to revolve it. Now this line right here is the line y is equal to x squared. So that is that line, okay? So that is the line, I'm sorry, the curve, it's not a line. That is the curve y equals x squared. So if I revolve this thing about the line segment AB, I can see that the line segment AB, I can describe it. Give me the equation of the line segment AB if I was to look at it as a full line. What would it be? So if I was to look at this as a full line, what would the line segment AB be a line of? What would it be called?
Is it x equals 2?
X equals 2. Thank you very, very much. So that's x equals 2. Okay, so now I'm going to revolve this thing, and I'm not really good at this. I told you guys I do the best I can. I'm a perfectionist, and so I have a hard time when my pictures don't come out the way they're supposed to. Whoa. Okay, that's the best I can do. Okay, so when we pick a point and revolve this thing, we get something that looks like that. Okay. So now you can see our disk. All right, so here's my disk. All right, and so that disk has a radius. So I look, here's the radius of the disk. I can only choose the part of the circle that's inside the domain that I'm looking at. So that's the radius of the disk. And I'm revolving it in the y direction. So this is going to be the volume, is going to be the integral from C to D of pi times my radius of y squared dy. Okay, now the reason why this one is a little bit challenging is because we have to figure out the radius. So I'm going to do something first just to help you figure out what the radius is. Suppose I give you this line and I tell you this is 2, this is 6, and this is 4. Okay, actually, that's not what I want. I don't want to do that. Good. I see somebody in the chat. Okay, thank you, Mikhail. Thank you very much. Okay, here's another line. That looks like that. Okay, so my question to you is, how long is that line?
Is it 2.5?
Okay, it's 2.5. All right, so one way I can do how long is that line is to figure out that if I take 4.5 and I subtract 2, I'm going to get 2.5. Okay, how long is this line?
1.5.
Okay, so it's 1.5. Because you took this length 6 and you subtracted 4.5 and you got 1.5. Does everybody see that? So for this line, she took 6, she subtracted 4.5, and she got 1.5. Okay, let's keep going. Here's another line. How long is that line?
Around 1.5.
Oh, we're not looking at nope, we got a whole new picture.
Will it be 2 minus x?
Yeah, this is a whole new picture, but thank you for your answer. Yes, this one is 2 minus x. How did you get that? You took the whole length 2, right? And you subtracted off x. Okay, so let's go back over to our picture. As we can see, this whole piece from here to here, that is 2. But now, wherever I choose to draw my thing, this value right here is x. So therefore, this length, if I draw a length from here to here, that length is 2 minus x. So that means that the radius of the circle is 2 minus x. But I already know my function, my radius has to be a function of y. So y is equal to x squared. So therefore, x is equal to the square root of y. So therefore, my radius, which is now a function of y, is 2 minus the square root of y. So that's how long this line is right here. It's 2 minus whatever x value that occurs. So I choose a y. When I choose a y, it has a fixed x. That length of x is 2 minus the square root of y, because I only want that little piece. All right, now y starts at 0. So I see y starts down here at 0, and y goes all the way up to 4. Because this is where y is equal to 4. Okay, so now I have my integral. So my volume, the integral from 0 to 4 of pi times 2 minus the square root of y squared dy. So that's the integral from 0 to 4 of pi. And I have to FOIL that. So I get 4 minus 4 the square root of y plus y dy. So that's when I'm integrating. So this is the integral from 0 to 4 of pi times 4 minus 4 y to the 1/2 power plus y dy. That's pi times 4y minus 4 I'm going to add 1/2, which is 3/2, and divide. So that gives me 2/3 y to the 3/2 power plus 1/2 y squared, evaluated between 0 and 4. Okay, and when you plug that thing in there, you get 8 pi over 3. And that's it. Okay. All right, we have one more of these. This one was on one of my tests a couple years ago. I like this because it's a cute problem. Okay, so I am going to let you guys figure this problem out while I take roll. So you can work on this one.
Dr. Light, can you go up just a little bit so I can get the end of the last?
All right, who wants to start talking through this problem? I'm not saying that you did the problem, you 100% got it right. I'm just saying who wants to talk about it. What does y equal x minus x squared look like? What kind of function is it? My daughter is in 10th grade algebra 2, and she is learning what these functions look like. What does y equal x minus x squared look like?
Wouldn't that be a parabola?
Okay, is it a parabola facing up or is it a parabola facing down?
It should be down because it's negative, right?
All right, man, Jaden, thank you. Awesome. Okay, so now how do I draw this parabola that's facing down? Do I know anything about it? Does it look like this? Does it look like this? Does it look like this? How do I know? What do I know about this parabola?
Doesn't it start from 0?
Okay, so I know it starts at 0 because 0 is on the curve. I see that. Can you tell me the other x-intercept? Do you know what that is? We're so close. Find the other x-intercept.
It would be 1, right?
It will be 1. Okay. So I have y is equal to x times x minus x squared. So I would get 0 is equal to x minus x squared, which is x times 1 minus x. That would tell me x is equal to 0 and 1 are my y-intercepts. So therefore, the parabola I want looks like this. There's my region. Okay. Now I'm revolving this thing about the x-axis. So that means choose an x. All right. Then since I'm revolving it around the x-axis, this thing's going to kind of look like a lemon. Because right here, I'm going to take and draw where it revolves around the x-axis. So I get something that looks like that. So now I can see my disk. That is weird that it wiggles when I draw in it. Okay, there's my disk. All right, so what's the radius of my disk? What's the radius of the disk? Radius of the disk is that height. What is that height? How tall is that?
Is it x minus x squared?
That's x minus x squared. Okay, so I think we're ready. We already know that this disk could be start way over here and be a small, so disk starts way over here where x is 0, and then it moves all the way through to x is 1. I know it's pi times the radius squared, which is x minus x squared dx. Pi times the integral from 0 to 1. I'm going to get x squared. I'm going to get minus 2x cubed. And then I'm going to get plus x to the 4th. That whole thing integrated dx. So this becomes pi. The x squared becomes 1/3 x cubed. Then I'm going to get minus 2/4 x to the 4th. And then I'm going to get plus 1/5 x to the 5th. That whole thing evaluated between 0 and 1. So this is pi. And in here, I'm going to get 1/3 minus 1/2 plus 1/5. And this answer comes out to be pi over 30. Okay. All right, I have one more example, but I think I'm going to go on to volume by washers. And then if we have time, we'll come back and do that last example. So we have C. Okay, volumes by washers. All right, does anybody know what a washer is?
Isn't it like a disc with the hole in it?
Okay, it is a disc with a hole in it. That is exactly right. So if you've ever had to replace a faucet or put a screw or something on a bike, or you're putting together exercise equipment and something's going to be moving and you don't want the screw directly up against whatever it is, you put a washer in. Okay, so a washer is that little metal disc. All right. And for a washer, it kind of looks like taking one circle like this and putting inside of it another circle like that. Okay. And so this is the washer. All right. So notice that if I find the center, the very center, I have two radii, okay, radius, plural of radius is radii. So I have two radii. I have one which starts here and goes all the way to the top. That's the big radius. We're going to call that R. If I can get that to be straight, I'll be happy. They just don't want to lay straight. I don't get it. Okay, so this is R, big R. And then I have another smaller radius that starts at the center and goes to the center of the other edge of the other circle. And that is little r. Okay. All right, so now to find the area of this, the area of the washer, we're going to take the area of the big circle and subtract the area of the inner circle or the little circle. Okay, so the area of the big circle, well, that's just pi times its radius squared. And the area of the little circle, that's just pi times its little radius squared. Now we already said, then now we know the area. So the area of the washer, and that is all of this. Whoa. Don't act up on me today. I don't have nothing to move. So this is the area. Take the area of the big circle and subtract out the area of the little circle. This is all you have left. Okay. Spend too much time drawing pictures here. All right, but I need that to be clear. Okay, so now the area of that washer is pi r squared, big R squared, minus pi times little r squared. And that's pi times big R squared minus little r squared. So now if we were stacking up a bunch of washers, we would have volume. Okay, so we stacked up a bunch of little washers, or think of it as stacking up donuts, flat donuts, we would eventually end up with volume. So we already said that our volume, again, we go back to our original equation, was integral of a of x dx. But anytime you see a washer, you know that you're going to use the integral from a to b of pi times the big radius of x squared minus the little radius of x squared dx. And if the washer is laying flat, then you would do the integral dy. Okay, so what might that look like? Okay, so here's my first problem. Oh, we are always in the way. Move us, move. Uh-oh. No, no, don't do that. Don't do that. Hmm. Okay, so we have to see the washer. The same way you have to see the disc, you have to see the washer. And so that's why I say draw the picture so that you can actually know what it is. Okay, so consider the plane region. That means it's flat, bounded by the curves x equals y squared, x equals y squared, or y squared equals x, and y equals x cubed. All right, so let's start off drawing that region. So when I go to draw this, the first thing I notice is I really don't draw y squared is equal to x. It would be easier for me to draw x is equal to y is equal to the square root of x. So we're going to do that. Y is equal to the square root of x. And then y is equal to x cubed. So y is equal to the square root of x looks like this. And y is equal to x cubed looks like this. What? Something is wrong. Okay, let's try this again. Thank you. Okay, so I have y is equal to square root of x and y is equal to x cubed. All right, so this is my region. So my region is everything in between. So there's the plane region. I can draw it. So first thing I've done is draw my plane region. And I want to revolve this region about the x-axis. So I'm going to do it just like that. Okay, I'm going to go right around the x-axis, the whole thing. So let's find an x. And the bottom curve will revolve like this. And the top curve will revolve like this. Oh, that's supposed to be red. Okay, it's not too bad. That's better. Okay. So now that I've chosen an X, when I look at this smaller curve, the smaller curve is going to revolve like this. And the larger curve is going to revolve like this. And you should be saying, I see the washer. I see the washer. Okay, so once you see the washer, you automatically know now this is volume by washers. Okay, so now we need to determine, one, where does it start and where does it end? So what are our limits of integration? Not given to you in this problem. we need to determine big R and little r of x. So those are the next two steps. So the limits of integration, well, I clearly know from the picture I'm starting at 0. The question is, I'm going all the way up to this point. So I need to know what this tick mark is. I'm going up to there. So my washer starts all the way down at 0, and then it pushes through all the way up to that point. So how can I find that value or the point of intersection? Again, I need to find the point of intersection. And the only way I can find the points of intersection is to find the points that are on both curves. So set them equal. So set y equal to the square root of x equal to y is equal to x cubed. So I get the square root of x, or y to the 1/2 is equal to y cubed. So I get y to the 1/2 minus y cubed is 0. Factor out y to the 1/2. And I get 1 minus y to the 5/2 is 0. So that tells me y is 0, or 1 minus y to the 5/2 is 0, but that implies y is equal to 1. So y is equal to 1. And if y is equal to 1, what is x equal? Okay, I think I just did that completely wrong. All of them supposed to be x's. This is x is y is equal to 1/2 and x cubed. I don't know how I did that, but these are all supposed to be x's. Okay, so the intersect with x's, so we get 0, x is equal to 0 and 1. Okay, so this location is 1. All righty. So here's our vi. Oh, so that was that. So what's our big radius? What's big R? What is big R?
Would it be the red line?
Yes, it is. And that curve is what?
Y equals square root of x.
Okay. So big R is the red one. So that's the square root of x. So by process of elimination, the little r is x cubed. So now we're ready to do it. Is the integral from 0 to 1 of pi times the square root of x squared minus x cubed squared dx. So this is equal to pi, the integral from 0 to 1 of x minus x to the 6 dx. So you get pi 1/2 x squared minus 1/7 x to the 7th. Evaluate between 0 and 1. So that's pi times 1/2 minus 1/7, which is 5 pi over 14. I think that's the answer. And that is right. That is right. That is right. That is right. Okay, any questions? So the big radius was the distance from here up to here. And a little radius was the distance from here. Why is it doing that today? From there up to there. Put that back. Okay. I'll give you a second to digest that. The integration on that problem was very easy. What time is it? I have 15, 18 minutes. I'll do 2 more. Okay. Find the volume of the solid generated by revolving the x-axis about the x-axis, the region bounded by the parabola y equal x squared plus 1, and the line y equal x plus 3. Okay, so we need to graph those. Let's see. I'll see if I can take y'all to my site, if this will work. Can I get y'all to go to my site here? No, I don't want to go there. This will work. Okay, can you see my internet?
Yes.
Okay. I can go to graphsketch.com. Oh, somebody put something in the chat. Okay, thank you. All right, so let's get rid of these ranges because they are way too big. So let's go with -5, -5, and get rid of this. Oh, let's reset everything. Oh, no, I don't want that. Duh. Go back to -5. I don't know why they give you -17. That's just so big. Okay, So the first graph I'm going to put in is going to be x squared plus 1. Where is my graph? Oh, it's spinning, guys. That's not a good sign. My minimum value of y. Oh, that's because this is supposed to be -5. All right, let's try it again. This is rather scary. Okay, there we go. Okay. And then the second one is x plus 3. Now, of course, I know how to do this. I'm just giving you guys another way of doing this. Okay, there we go. All right, so as I can see, I really need to go only between -1 and, all right, so let's increase the y range a little bit. Maybe make it, I don't know. What does it go up to now? 5? Maybe let's see if it goes up to 7, if I can get the whole thing. I would have done faster plotting this myself, but I thought this would be cool. Okay, there we go. Click here to download this graph. I have it. It's now mine. I can open it. There it is. I can copy it and I can stick it right into my problem. There we go. All right, how cool is that, guys? There's my graph. All right, so this red line is y is equal to x plus 3. And the blue line is y is equal to x squared plus 1. Now, from this picture, you can clearly see the limits of integration. The limits of integration are here. This is 1, and then this is 2. So we can see the limits of integration are 1 to 2. If you can't see that, yikes. If you can't see that, you can set them equal. So you can get x squared plus 1 to equal x plus 3. And then you get x squared minus x minus 2 is equal to 0. So you factor it and you get x minus 2 times x plus 1 is equal to 0. So you get x.
That's a lot.
This should be -1. Is that what you're going to tell me?
No, I just only see the graph. I don't know what you're writing down.
You don't see what I'm writing?
No, it's only showing like
Oh, I forgot to go back to where, I'm sorry, guys. Thank you. Thank you. I forgot to go back. You got it. Yeah, I forgot. Okay. I got a whole new world over here. I done wrote a ton of stuff. I'll give you a minute to catch up. I'm sorry. Thank you. Thank you. Okay. So now I know my limits of integration. I could see from the graph that they were -1 and 2. But if I couldn't see that, I proved that they were -1 and 2. So now I know my limits of integration. Okay, so limits of integration. I'm on the interval -1, 2. Okay, now I need to revolve these. So choose any X you want. Doesn't matter what X you pick. I'll choose this X. This is fine. Okay, so now when I revolve this, the blue curve is going, see, it's at 2 and 1. So the blue curve is going to look like this, and it goes all the way down to -5, which is not even there. But yes, it is. There's -5. So that's the blue curve. And then the red curve is going to go like this. And so my X that I chose is going to have one, I don't want that red. It's having trouble with its colors today. For catching up with me, that's what the problem is. Please don't tell me it's frozen. Okay. It is not happy with me. Okay. So the radius here and then the radius at that same point there. And there I see my washer. Okay. All right, so therefore the volume, the integral, I know I'm going to go from -1 to 2 of pi times the big radius squared minus the little radius squared dx. So what's the big radius? Well, that's the red one, x plus 3. And the little radius is x squared plus 1. So this volume, the integral from -1 to 2 of pi, I'm going to have x plus 3 quantity squared minus x squared plus 1 quantity squared dx. (17 pi over 5), 117 pi over 5. Okay, I want to do one more. Okay. Okay. All right. So this region is bounded by the parabola. This is a nice, easy one to graph. Y is equal to x squared. And the next one is the line y equals 2x. And they do tell you in the first quadrant because these two things can be in other locations. So they tell you in the first quadrant. All right, so this is y is equal to x squared. And the blue one is y is equal to 2. Oh, blue one, blue is y is equal to 2x. And so here's my region. It's that little yellow spot there. And I want to revolve this about the y-axis. Notice it says in the first quadrant. So I know exactly what piece, because this thing goes down, and it's crazy wide if I don't include that. Okay, so the red looks like this on the other side. And the blue looks like that. So now when I revolve it, I'm going to choose a y. And now this is going, I don't like that color. Give me gray. This is going to revolve like that. And then this and now you see my washer. Okay. So I can see that my washer starts down here at 0 and it goes all the way up to this value of y, which I don't know. So let's check. So I have y is equal to 2x, and that also has to equal x squared. So I get 2x minus x squared is 0. So I get x times 2 minus x is equal to 0. So I get x is equal to 0 and 2. But I'm trying to find y. So when x is 0, y is 0. And when x is 2, y is 4. So this value is 4. So my limits of integration are 0 to 4. Okay, so now the radius has to be a function of y now. Okay, so it has to be a function of y, not a function of x. So that means I need to change this to x equals the square root of y. And I need to change this to y to x is equal to y over 2. Okay. So see, here's the big radius. Goes to that curve. And then the little radius, which should be blue, goes there. So the volume equals the integral from C to D of pi times r of y, big Y, r squared minus little r of y squared dy. So that is the integral from 0 to 4 of pi. Big R of y is the square root of y. And little is y over 2 dy. And if you compute that, you get 8 pi over 3. Okay, questions, comments? We have one more technique to learn. Oh man, Dawn. Oh no, you're good. One more technique to learn, and that is volume by shells. And I want you to think soda can when you come in on Monday, because that's what we're going to be looking at, soda cans. Okay, any questions about any of this?
I have a question.
Yes,
So I know that our last homework is on shells.
it should not be due to that. Yes, the last which last homework? Hold on, let me
I think
look.
it's 2.2, I think.
Let me look. What happened to my Edgefinity? Hold on, my Edgefinity closed.